What I want to talk about in this video is one of the simple and straightforward applications of matrices. So, in this regard, I'll be talking about simultaneous linear equations. So, matrices can be used to understand or rather to solve system of linear equations. So, if you have let's say this example where I have three equations and three variables x, y, z. So, I have three linear equations. So it's a system of linear equations, and there are three variables x, y, z. So the first equation is 2x plus 3y minus 3z is equals to 17. The next is negative x minus y plus z is equals to 5. And the third equation is x minus z is equals to negative 19. I don't have a y variable here. It doesn't matter. This is a system of three equations in three variables, linear equations, three variables. So uh, in this video, I'll just show you how to represent a system using matrices, and in further videos, I'll show you how you can solve the system using properties of matrices. So this video is just about representation. I'll just show you how to represent a system as a matrix. So this is just about representation. So what you do here is you first construct the coefficient matrix. So you have a 3 by 3 you have three variables and three equations, right? So you create a 3 by 3 matrix wherein the first row is concerned with the first equation, the second row is concerned with the second equation, and the third row is concerned with the third equation. And with regards to the column, the first column is concerned with one of the variables, let's say x. The second column is concerned with the other variable, let's say y, and the third column is concerned with the other variable, let's say z. So if I have to worry about this entry is nothing but the first equation x columns coefficient, x variables coefficient. So the variable x here has coefficient 2. So this entry is, I'll make it at 2. Next, this represents the first equation y variable. So this is nothing but the first equation y variable coefficient. So it's 3. This will be the first equation z variable coefficient. So it is negative 3. So if I have a negative outcome, you consider it as a negative 3. The coefficient is negative 3. And similarly, you do with the other two equations. The second row represents the second variable, second equation. So the first entry here will represent the coefficient of x, which is a negative 1 in this case. The coefficient of y is again negative 1, or minus represents a negative, and the coefficient of z is positive 1. No coefficient is there, so that means I can assume it to be a 1. The last row represents the third equation, and in that the coefficient of x is 1. Now I don't have a y variable here, but I can say it is a 0 y, right? I can have a 0 y. Anything multiplied by 0 is 0, so it's as good as having a coefficient of 0. So the coefficient of y is 0 here, and the coefficient of z is minus 1. So this is my coefficient matrix, and I can call it this is A. This is my matrix A, coefficient matrix. Next, this is the crux of this representation. Now again, you will realize why we define matrix multiplication the way we did it in the previous video. What I'll do is I'll now represent the variable matrix as a column matrix, and these are nothing but the variables that are used, x, y, and z. So what I'll do is x, y, z will be the entries in this column matrix. So this is my variable matrix. I'll denote it with a capital X. Denote it with a capital X. And now if you see clearly that if you multiply these two matrices, first of all, multiplication is valid in this case because this is a 3 by 3 matrix, and this is a column matrix, so it's a 3 by 1 matrix. These inner dimensions match, so yeah, this matrix, these matrices can be multiplied, and the result will be the outer dimensions. It will be a 3 by 1 matrix. So if I were to write it like this, It will be a 3 by 1 matrix, and let's see what the first entry in this result will be. Uh, just recall what matrix multiplication is. It's nothing but this row multiplied by this column. So if I were to take a 2 multiply with x, I'll get a 2x. So it's 2x. Then a 3 multiplied by y. So I have a positive 3y plus 3y. And a negative 3 multiplied by a z. So it's minus 3z. Minus 3z. So this is my first entry. And the next entry is a negative 1 times x is a negative x. Negative 1 times y is negative y. Minus y rather. And 1 times z is just plus z. Next I have 1 times x, it's x. And I have 0 times y, so I can even write it 0 times y. No harm in that. And a negative 1 times z is negative z. And this is my column matrix. This is my 3 by 1 matrix the product multiplication of these two matrices. And what you'll realize is these are nothing but the left hand sides of my linear equations, right? So you can see clearly that 2x plus 3y minus 3z is actually this. And according to my linear equation, this expression equals 17. So this is nothing but I can replace this with this entry can be replaced with 17. Similarly, this is nothing but the left hand side of the second equation, and it equals 5, so I can replace it with a 5. And this entry, this is nothing but the left hand side of my third equation, so I can replace it with a negative 19. So yeah, if I say this is my another matrix, let's say B. What I have done is now I have represented my system of linear equations in a matrix form. So I can say this is my matrix A, which is my coefficient matrix multiplied by my variable matrix X, giving you the RHS value, the right hand side value is equal to this B. So this is matrix multiplication. I have A matrix multiplied by X matrix giving you the B matrix. So this is how you represent a system of linear equations in matrix form. And then we'll see in future videos how you can use the theory of matrices to solve for these variables X, Y, Z.